The weight average molecular weight is another parameter that's used to characterize chain length in polymer systems. So let's take a look at how we would calculate this using the general rule that I proposed, where I said that the x average of y is equal to the sum over the distribution of the product of x of each y times y over the total x. So notice that in this framework, then weight corresponds to x and y corresponds to molecular weight. So by that rule then, the weight average molecular weight is the product of the weight of molecules that have molecular weight mi times the molecular weight mi divided by the total weight of molecules in our sample. So let's take a look at how we could calculate this for our polymer sample that has a distribution of molecular weights that's shown here. So again, we've divided this into 8 bins of different molecular weight ranges, and the number of molecules in each of those bins is shown here as N1, N2 up to N8. So by this relationship then, the weight average molecular weight is the product of the weight of molecules with molecular weight mi times molecular weight mi. So I have the weight of molecules that have molecular weight m1 times molecular weight m1 plus the weight of molecules that have molecular weight m2 times m2 and so forth up to w8 times m8. And then in the denominator, I have the total weight of molecules. So I have the weight of molecules that have molecular weight m1 plus the weight that have molecular weight m2 and so on up to the weight that have molecular weight m8. So then I can capture this in the form of a mathematical equation as follows. The weight average molecular weight is equal to the sum over the distribution of the product wi mi over the sum of the wi, where wi is the weight of molecules associated with each of these bins in my distribution. Okay, so let's see if we can cast this in a more familiar way by noticing that the weight of molecules in each of these bins is equal to the product of m1 times n. So how can we see that? So m is the molecular weight, so that's grams per mole, and n is the number of molecules that have that molecular weight, so that is a number, and that would be in terms of moles. So moles times grams per mole gives us the weight in grams. So the product n times m is equal to these weight fractions. I can substitute this then into the equation for the weight average molecular weight, and I obtain an equivalent relationship where the weight average molecular weight is the sum of the product of ni mi squared divided by the sum of the product ni mi, and those are added up over all the bins in my distribution function. That's the weight average molecular weight. Now this kind of average is a little bit different. Notice that it weights the heavier fractions in the distribution more strongly, so it skews it in a different way. To connect with the class average example that I proposed for the number average molecular weight, remember that's just averaging the number of students that got a certain grade on an exam and then dividing by the total number of students. This would be, maybe you could think of as if you have a grade distribution for term papers, and instead of calculating the number average, you put the term papers on a scale and weigh them. So then your distribution function for each grade, you have a total weight of papers that had a grade of 85, or a total weight of papers that had a grade of 90. And then you add up all those and compute an average that's skewed or influenced by the length of the paper, if that's representative of the number of pages in the report, something like that. So instead of the number of students, it's related to the mass or weight of what was the product that was produced, something like that. I don't know if that's helpful, but that's kind of the way that I think of it.